When even a Nobel laureate in physics expresses doubt about how our understanding of the universe, it is clear that we have entered a new astronomical era. However, Adam Reyes is not alone in feeling uneasy. The James Webb Space Telescope is discovering more and more structures in space that defy traditional cosmology. How is it possible that galactic formations previously thought to be completely impossible are confirmed to exist? These puzzling findings raises questions about the future of our research and whether our previous theories have come to an end. Seemingly simple questions require complex answers. For example, the question of the expansion rate of the universe, although seemingly straightforward at first glance, touches the core of a mystery that has perplexed experts for years. It is accepted that the universe has been continuously expanding since its origin approximately 13.8 billion years ago, which means that galaxies are moving away from each other at a rate proportional to their distance. In other words, if a galaxy A is twice as far away from Earth as galaxy B, then its rate is receding is also twice as fast. Edwin Hubble, an American researcher, was a pioneer in identifying this correlation. To calculate the rate at which two galaxies are moving apart, it is necessary to know their distance and constant that multiplies that distance, what is known as the Hubble constant. This is where things get a little bit complicated. There has been a considerable controversy among experts about the exact value of this constant. Previously, measurements have yielded conflicting results, indicating that the results depend on the measurement method used. One method for measuring the expansion of the universe is based on the cosmic microwave background radiation, which is a near-isotropic fingerprint of the early universe and is considered strong evidence for the Big Bang theory. Using this radiation to calculate the expansion rate yields a value approximately 60 kilometers per second per megaparsec. To put this in context, 1 megaparsec is equivalent to 3.26 million light years, and 1 light year represents about 9.4 trillion kilometers. On the other hand, if we measure distances in space using so-called cephesoids, a type of star that exhibits periodic fluctuations in brightness, the expansion rate rises to 73 kilometers per second per megaparsec. This suggests that the universe is expanding faster in our vicinity, for example, up to 3 billion light years compared to the total expansion. This discrepancy between the two values is known as the Hubble strain, and so far, no researcher has been able to explain this unexpected variation. The James Webb Telescope has turned its attention to this enigma. Some scientists previously speculated that the mystery related to the expansion rate might be due to a measurement error of the Hubble Space Telescope. Adam Reyes was also interested in determining whether there were any errors in the Hubble data. This physicist from Johns Hopkins University, who received the Nobel Prize in Physics in 2011, along with other researchers, had shown that the expansion of the universe is accelerating. Reyes and his team used the James Webb Telescope to investigate the causes of this discrepancy in the Hubble expansion and look for possible errors in measurements. To understand how the expansion of the cosmos is determined, the so-called cosmic distancer ladder is used. Each stage of this ladder builds on the previous one, which means that a possible error in the measurement can affect all stages. However, the methods mentioned above only prove to be reliable to a certain extent. This is because, as the distance increases, it becomes more complicated to measure accurately. The reason is that the light from the stars mixes with the light from other stars, making it difficult to observe. However, the James Webb Telescope is 100 times more powerful than the Hubble telescope, allowing experts to peer farther and further in great detail than ever before into the farthest secrets of the universe. In a study published in the Astrophysical Journal Letters, a rather revealing picture was presented. The James Webb Space Telescope scanned the entire area previously observed by Hubble and found no errors in the measurements. Therefore, the Hubble strain problem persists. Adam Rees offers a brief but profound explanation. It could be that we have simply misinterpreted the nature of the universe. We must now investigate whether we have missed something in our previous investigations and how we can connect the origin of the cosmos with the present. This solution could put Einstein's theory of gravity to the test. However, researchers working with Adam Rees are not the only ones tackling the confounding Hubble tension. Scientists at the University of Bonn and St. Andrews are also exploring this mystery and have proposed a new possible explanation. In detailed terms, our planet lies in a bubble-shaped region of space, where there is relatively little matter. The density of matter is highest in the vicinity of this bubble, and the gravitational forces emanating from that matter pulls galaxies towards the edge of the bubble. As a result, these galaxies are moving away from us faster than expected. This explanation is plausible, but it leads to another research dilemma. Why does the standard model not predict the existence of such bubbles, or structures should not really exist? Instead, matter should be uniformly distributed in space. The standard model is based on Albert Einstein's theory of the nature of gravity, but it is impossible that gravitational forces behave differently than Einstein predicted. For this reason, scientists have considered a modified theory of gravity proposed by Israeli physicist Mordechai Migron in 1980s. However, the so-called modified Newtonian dynamics has not yet achieved accepted status, even though it accurately predicts the existence of these bubbles. If gravity really behaves according to Migron's ideas, then all discussions about Hubble tension could be left in the past. In this new context, there would be only a constant for the expansion of the universe, and the observed discrepancies would result from irregularities in the distribution of matter. Time will tell how accepted and confirmed this approach will be, but a review of the cosmic past reveals how much remains to be understood about the future. Sometimes a single piece of information can stunt even the most experienced astronomers. For example, the record redshift of the galaxy JADIS GSZ 1440 indicates that this gravitationally bound group of stars already existed 290 million years after the Big Bang. At the same time, the oldest known galaxy raises intriguing questions. How could it have been so bright and massive at that time, and where did the necessary matter come from? Thanks to the Webb telescope's NIRCam near-infrared camera, it's been possible to discover that this structure probably took 100 million years to reach its current size. The bottom line is that this infant galaxy defies virtually all theoretical models and computer simulations of the early cosmos. In fact, the galaxy is in good company. 6 galaxies that the James Webb Telescope added to star maps in early 2023 also turned out to be much more massive than expected. Although these structures existed when the universe was only 500 to 700 million years old, they resemble today's Milky Way. Since this seems impossible according to conventional cosmology, these galaxies have been dubbed universe breakers by experts, in contrast to baby galaxies that were expected. Researchers have observed impressive objects, all with more than 10 billion solar masses of stars, and one of them may even have more than 100 billion solar masses. The question now is, how was this possible? Now just imagine, if any of these galaxies turned out to be real, it would push our understanding of cosmology to its limit. To explain the existence of these structures, the density of matter in the early cosmos would have to have been up to 5 times greater than our models suggest. Alternatively, these galaxies could have developed in ways we do not yet know. These findings raise the need to rewrite from scratch the history of the early universe and possibly the Big Bang theory itself. Let me know what you think in the comments box. If you liked the video, remember to hit the like button and subscribe so you don't miss out on more content like this. Thank you so much for watching, and I'll be seeing you in the next video.